Mute it. Sorry. Okay. Can you guys hear me now? Where's the chat? Chat. Okay. Okay. Cool. So you've probably heard that everything on a computer is just zeros and ones, which is called binary. So this is basically the easiest way to store information reliably, because you only need to know if an electrical signal is on or off. You don't need to know how much power it has. So there's a lot of room for error there. Um, and it just makes building computers a lot simpler when you don't have to deal with that. So how does this actually work? That's what we're going to start getting into. So the number system we're used to is called base 10, which is also called decimal. So every digit has a place value, which is 10 times the value of the previous digit. So place value here means that it's sort of how much that digit is worth. So for example, if we have the number 125, the actual value of this number, 5 has a place value of just 1, like because it's in the ones position. So that's 5 times 10 to the 0, which is 1. 2 has a place value of 10 because it's in the tens position. So it has so we'd say we have 2 times 10 to the 1, or 20. And then 1 is in the hundreds position. So we'd say it has a place value of 100. So if we wanted to find the value, we'd say 1 times 10 squared, which is 100. So if we wanted to find the actual value of this number, we'd do this and add it all together. So we have 100 plus 20 plus 5, which probably seems pretty obvious if you're thinking about this in base 10. But the main observation is that we could just switch this 10 to something else and use a different base. So binary is what we call base 2. So it works basically the same as base 10. We just switch the 10 to a 2. So for example, if we have 1, 0, 1, 1 in binary, now instead of using a 10, we use a 2, but the rules are still all the same. So here we have 1 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 to the 2, and then 1 times 2 to the 3. So we do the same thing where we increase the place value from 0 from right to left, but we just change it to 2 instead of 10. So base 10 has 10 digits for 0 to 9, because after 9, we get the first 2-digit number. Similarly, base binary only has 2 digits, which are 0 and 1. So does this make sense so far? Does anyone have any questions? Okay, just check chat quickly. So the term bit is short for binary digit, which just means a single 0 or 1, and a byte is 8 bits. So on most computers, a byte is the smallest unit of memory that you're allowed to directly work with. So this is why file sizes, RAM size, and all that kind of stuff is usually measured in bytes. So the issue with binary is that it gets really, really long really quickly. So since there are only 2 digits, you need a lot more digits to represent more than a tiny amount of data. So for example, just 4 bytes of data already takes over 30 binary digits to write out. And you can imagine this is a huge inconvenience for dealing with large amounts of data. Like you probably have files on your computer that are millions or billions of bytes long, which is a lot. So our solution is these other number systems called hexadecimal and octal. So just like we switch from 10 to 2 to get binary, we can switch our base to other numbers too. So base 16 is called hexadecimal, or just hex for short, and base 8 is called octal. And then just a side note, since we need 16 digits for hex, we use A to F for digits 10 to 15. So that's just because you can't just put 10 there because 10 is a 2-digit number. Does that make sense so far? Any questions? All right. So how does this solve our problem? So any system based on a power of 2 can easily be converted to and from binary. So for base 2 to the n, for any n, each digit in that base is exactly n bits, which means that we can just convert between digits in base 2 to the n and groups of n bits individually. So this basically lets us use hex and octal sort of like compressed binary. And we'll have an example of that on the next slide. So let's say we have the hex number 4A. We can actually write this out over here. Uh, can everyone see if I write over here? Okay, just erase a little bit more to make space. So if we start with 4, oh god, sorry, 4A. Oh, this chalk is really bad, I'm sorry. Can you guys see okay? All right, so what we basically can do is just take each digit individually and convert it individually into binary. So 4 is just 0, 1, 0, 0. Going over it again so you can see. And A is 1, 0, 1, 0. Because A is 10, and this is how you'd write 10 in binary. And then you just combine them together. So from here to here. So the final thing we get is just 0, 1, 0, 0, 1, 0, 1, 0. Does that make sense? So it's a lot easier than converting from decimal to binary, because to convert from decimal to binary, you have to convert the entire number at once. You can't take the shortcut where you just split it up by the digits. And then octal is similar. You just use groups of 3 instead of groups of 4. So an important question is, how do we know what base a number is in when we write it? Because if you look at this right here, this could just be, I wrote 100 here, right? You wouldn't know immediately that this is supposed to be binary. You could probably guess, like, if there's a lot of ones and zeros, it's probably binary, because you're probably not just going to coincidentally have a really big number that's all ones and zeros. But in general, like, if you have a number like 1, 1, that could be saying 11, or it could be 1, 1 in binary, which would be 3. So you have to have a way to know which one it is. So a common convention that's mostly used in math is to use a subscript. So 1, 1 with the subscript 10 would be base 10, and 1, 1 with the subscript 2 would be base 2 or binary. And if there's no subscript, we just assume it's base 10, like a normal number. So the issue is that doesn't really work too well on computers, because you can't always write a subscript. Like if you're programming, or if you're sending a text message or something like that, you can't really type a subscript. So it's common to use these prefixes instead. So use the prefix 0b for binary. So you can do like 0b 1101, 0x for hex. So like here we have 0x1ac. And for octal, it's a little weirder. There's either 0o, and then there's some programming languages like C where you just put a leading 0. So like this 0755. Um, Yeah, so almost all programming languages will recognize these, with octal being the weird one, where like some programming languages recognize one, some recognize the other. And like before, we usually just assume base 10 by default. So any questions about anything so far? Yep. Yeah, so octal is not used very often at all. That's why we didn't really talk about it much, but um, it's used a little bit for permission systems on Linux, which we'll get to later. But other than that, I can't think of like a single time I ever used octal. Yep.
So do the letters used in hex just represent like certain combinations of numbers?
You mean like the A and the C? Yeah, so A, B, C, D, F just represent the digits 10 through 15. So A just means like 10, but as a single digit. Because if you wrote out 1, 0, that would mean like something different in hex. Yep. Any other questions? All right. So that system tells us how we represent numbers on computers. The next question is, how do we represent text? So we can assign a number to every character, and then we just represent text as numbers. So a string of text just becomes a list of numbers. So the most common system for English is called ASCII, which stands for, I think, American Standard Code for Information Interchange. You'll never have to know that. Each character is assigned a 7-bit number. So ASCII has 2 to the 7, which is 128 characters. And even though ASCII characters are only 7 bits, we usually just use a whole byte on modern computers because it's just a lot easier than splitting things up between bytes. So this is the entire ASCII table. This projector doesn't, the screen doesn't go all the way down, so it's cut off a little bit at the bottom. But um, yeah, make sure you memorize all of this, will be important. All right, so just to be clear, that was a joke, but in all seriousness, there are some useful tips and tricks that you can remember to sort of remember parts of the ASCII table. Um, so it has a lot of patterns that are designed to be easily visible in hex and binary. So it's really common to use hex to write the number of an ASCII character. Um, so for example, the characters for the digits 0 to 9 are just hex 30 to hex 39. So basically in hex, if you want the ASCII character code for a digit, you just add 3 in front of it. That's it. Uppercase letters are hex 40 plus the index of the letter starting from 1. So A is hex 41, B is hex 42, etc. And then lowercase letters are exactly the same, but you start at hex 60 instead. And that means that every lowercase letter is exactly hex 20 after its uppercase version. Yep, sure. You good?
Yes.
Any other questions? All right, I'm just gonna check the chat real quick. So ASCII has a bunch of characters which are called control codes, and these are characters that don't actually represent a symbol. They just instruct the computer to do something. So most of these control codes are obsolete. Um, so there are control codes like for acknowledging messages or other stuff that's used for teletypewriters, where they're just used to like send a signal for your typewriter to communicate with the computer like on the other side of the building or something. They're not really used on modern PCs. But some control characters are still useful. So for example, the new line character is obviously pretty useful. You use that every time you hit enter. And also tab is still useful. So that's for like indentation, stuff like that. Um, so these are characters that you frequently find on text and that you can type on a keyboard. But if you really think about it, they don't correspond to any actual symbols. They just tell the computer to move the cursor, which is why they're considered control characters. Any questions about that? All right. So all characters below hex 20, which is 32, are control codes. And there's also a bonus one, which is the last control code, or the last ASCII character is hex 7F or 127, which is delete. And it's the only control code which is not in this range. So if you have a list of bytes where some of them are control codes and they're not like new lines or tabs or stuff like that, then you can probably take a guess that it's not going to be ASCII text, because it would be pretty weird if you had a bunch of those control codes in your text. And this isn't really super important, but it's kind of funny. Wikipedia has this note about the space character in its article about control codes. And I like this description a lot because it sounds like someone describing what space is to an alien. So it says space is a graphic character. It has a visual representation consisting of the absence of a graphic symbol. It causes the active position to be advanced by 1 character positions. In some applications, space can be considered a lowest level word separator to be used with the adjacent separator characters. Yeah, so not really relevant, but kind of funny. So what about other characters? 128 characters is not really that many, especially when we used up the ton of them for control characters that no one uses anymore. So it covers pretty much everything on your keyboard, but we want other languages. We want to have special symbols, emojis, stuff like that. So today we have a larger system called Unicode, which gives us way more characters. Um, and Unicode gets a lot more complicated than just characters. Not everything in Unicode is really like a character you can print out and display on your screen. So they're called code points instead. And there's some like displayable characters that are actually multiple code points, for example. So like, have you ever heard of like flag emoji taking up 2 characters on Twitter? This is why, because flag emojis are actually 2 Unicode code points next to each other for the country code of whatever flag the country is from, or whatever country the flag is from. And for backwards compatibility, the first 128 Unicode code points are exactly the same as the ASCII ones. Yep. Um, right now, I don't know. They add new ones all the time, so because they add new emoji all the time, so or not every new emoji, but a lot of new emoji are new Unicode code points. So Unicode code points can be up to 21 bits. Not every 21-bit number is an actual valid Unicode code point. Not every 21-bit number has actually been used yet, because we haven't run out of new Unicode characters yet. So we can fit every code point into 4 bytes easily. This encoding is called UTF-32. So this is the most obvious way to encode Unicode. This is sort of like what you would probably do for ASCII without even thinking about it. But most code points we use are actually really small. So UTF-32 wastes a lot of space. So because of that, we have more efficient encodings. So UTF-8 is the most commonly used encoding. And in UTF-8, numbers with less than 8 bits are just stored in 1 byte as is. Larger numbers have some bits at the beginning to indicate how many bytes they need. So for example, if a number needs 2 bytes, it'll start with 2 1 bits and then a 0 bit to let you know it needs 2 bytes. And then each continuation byte starts with a 1 0. So that's technically not necessary, but it allows you to easily tell if you're in the middle of a code point. Like if you just get a pointer to some random part in the middle of some UTF-8 text. And a really important thing is that because of the second bullet point that numbers with less than 8 bits are all stored in 1 byte, all valid ASCII text is also valid UTF-8. So it's completely backwards compatible with ASCII, which is pretty important. And then we also have UTF-16. So this mainly exists for historical reasons. Originally, a long time ago, Unicode was going to just be 16 bits, but then they ran out of space in Unicode really quickly, so they had to expand it. So what originally, this is basically like the original UTF-32. This was supposed to be like the really straightforward way to represent Unicode stuff. So this is used internally by Windows because they made the decision like 20 something years ago to use UTF-16 before Unicode got expanded. Now they're sort of just stuck with it. Code points larger than 16 bits are represented by special surrogate pairs. So this is a little convoluted compared to the way UTF-8 works, but basically there's like some values that are reserved in Unicode that like just cannot be Unicode characters because they have to be used by the system. So like there's some values in UTF-16 where if you encounter this value, you have to also check the next value, and those two together make one character. It's pretty weird. You're probably never going to need to know this, but any questions so far?
Wait, so if you have surrogate pairs, then why would you ever need
Um, what do you mean?
like if it already supports code points larger than 16 bits, why would you need 32 bits?
Well, all of them support code points that can be like up to 32 bits. So you can encode anything in any of these 3 encodings. It's just that The point of UTF-32 is like the most straightforward to implement, and it's also like every code point is exactly the same size. So if you need to access like the 1000th code point, you know exactly where it is without like scanning through an entire array of code points. Whereas with UTF-8 and UTF-16, the smaller code points take up less space, so you don't necessarily know exactly where the 1000th code point is going to be without going through every single one. Any other questions? Yep.
So is there the advantage of using UTF-16 that each character takes up less space? So if you have some sort of space or memory problem, you might want to use UTF-8 or UTF-16.
Yeah, so UTF-32 is like very, very rarely used. It's almost never used. It's just like worth mentioning because the most it's the most straightforward one and it technically exists. Realistically, almost everyone just uses UTF-8 because most text that we actually use is ASCII, and ASCII is really efficient in UTF-8 compared to UTF-16. Because UTF-16, everything has to take up 16 bits when most text we send only takes up 8.
So most of our text is UTF-8, and then if you want to put an emoji, that would be UTF-8.
No, so UTF-8, we can just go back. UTF-8 has ways to encode larger code points. So if you wanted to do an emoji, it would use this system here where you have like, let's say you have a 3-byte emoji, it would start with like 1110 to indicate that you have 3 bytes coming up, and then you'd have like the whole code point for the emoji after that. So like pretty much all the text you send and everything are probably UTF-8. Any other question? Yep.
So if you're already using, like you said in that example, you're using like 4 bits to start.
Right.
If the emoji requires 3 bytes, then wouldn't that like overflow like halfway to another one, like at the very end?
Yeah, so that is also one small advantage of UTF-16 is that in some cases there are some characters like that where UTF-8 needs 3 bytes to fit them in, but UTF-16 can do it in just 2 bytes because it doesn't have the overhead of those bits at the beginning. Um, but like most of the time, most text we send is just small enough that it just fits in 1 byte anyway, so it doesn't really matter. Any other questions? All right, so that covers how we represent numbers, how we represent text. I'm just gonna check some chat real quick, see if there's anything. Oh, okay. So now we have to get to how we represent other types of data, like images, songs, videos, etc. So generally, we think of data abstractly as just being a list of bytes. So files are basically just all big lists of bytes. So a file format like MP3 or JPEG is sort of just a description of how we interpret these bytes as meaningful data. So now the important question is, how do we actually read and write some arbitrary data as humans? So like, for example, if we know that a file is a video file, we might have a video editor that we can use to like look at it, edit it, stuff like that. But if we just have a file, we don't know what it is. It could be like literally anything. How do we take that, look at it, and edit it, right? So each hex digit is exactly 4 bits. So with 2 hex digits, you can represent a single byte. And for a list of bytes, you can just put the hex digits one after the other, and this gives you a hex string. So for example, if we take the hex string 89504E47, this corresponds to the bytes 89. So first byte would be hex 89, second byte would be hex 50, third byte would be hex 4E, and the fourth byte would be hex 47. So it's basically just a really it's basically just like a human readable way of representing some random binary data. And so hex editors are basically like special file editors that represent an entire file as a really big hex string and let you like edit the individual bytes. Any questions about this? All right. So hex strings are good if you want to interpret or edit your data in some way. But sometimes you just want to send data over something that only supports ASCII text. So like maybe if you have some sort of messaging app that doesn't support file attachments and you want to send a file over it. Um, so hex strings are pretty inefficient because you need 2 characters for every byte. And the alternative is base64, which is essentially another number system, but we don't usually think of it that way. So base64 uses 64 ASCII characters, which are all 52 lowercase and uppercase letters, all 10 digits, the plus and the slash. So this is sort of like how with base 16 or hex, we had to add in the letters A through F in order to get the digits 10 to 15. In this case, we need the digits 10 to 63, so we add in a lot of other stuff. So there are also alternate character sets for base 64. The most common alternate one is URL safe base 64, where you can't use plus and slash since those have special meanings in like website URLs. So they use like minus and underscore instead. So those are actually used for YouTube video IDs. So if you ever look at the URL for a YouTube video, the last few digits are base 64. So 64 is 2 to the 6th. So each base 64 character corresponds to 6 bits of binary. And that means 4 base 64 characters store 3 bytes, as compared to you would need 6 characters to store 3 bytes for a hex string. So it's much more efficient than a hex string. And then we use the equal sign character to pad base 64 strings to a multiple of 4 bytes. This is not technically necessary. You could just have it without any padding, but most programs do this just to make decoding easier. Any questions about this? I think there's an example on the next slide. Okay, wait, there isn't. Anyway, so being able to recognize hex and base 64 strings quickly is pretty helpful since both are very common. So hex strings only have digits and the letters A through F. And also since case doesn't matter, usually all the letters are in the same case. So it's sort of a pattern you can recognize to see like if I have a string that looks like that, it's probably a hex string. And then base 64 also has a pretty recognizable character set. So there's a mix of uppercase and lowercase letters, digits, and then the plus and the slash. And then there's also the equal sign padding at the end, which if it's there is a pretty good giveaway, but it's not always going to be there, so you can't rely on it. Yep. It does use numbers. There's digits here. Any questions so far? All right. So tools. We almost never convert between different representations by hand. That would be really painful. You can find websites to handle basically any conversion you want easily. So for example, if you want to convert a number to hex, or if you want to convert like a hex string to whatever the actual value should be, you can just Google it and you'll usually find a website that'll do it for you. You can also do these conversions in Python. So if you're familiar with Python, this might make sense to you. Bytes like objects have a hex method. And for the other direction, there's a byte.from hex function. And then there's the base64 module, which has b64 encode and b64 decode functions. If you're not familiar with Python, don't worry about that. We'll go over it later in more detail later on. So there's a quick example. So try to figure out what these 3 things mean. I'm just going to paste them into Discord so you don't have to copy them by hand. Right, so they're in the beginner workshop channel in Discord. Is anyone not in the Discord, by the way? Okay, good. It's in the channel called Beginner Workshops over here.
I don't see it. I know you have to sign up for different like roles and stuff. Is there like, is it specific to one of the roles?
Um,
Tasty.
what?
Tasty.
Tasty?
Last word. No, I don't want to give it away.
Oh, yeah, I see. Um, I think Discord added this browse channels thing. It might hide some channels by default. That might be it. That's pretty annoying if it's that. Yeah, there's no role for it.
Yeah, the browse channels, it shows up. It's just unchecked.
Yeah, okay, that's pretty annoying. I don't know why it's unchecked by default, but I'm just gonna put it in general because this is annoying. Okay, I put it in general too. I don't know why Discord hides that channel by default. That's really annoying, but if anyone couldn't see it before, it should be here now.
I think it might be without echo. The first string I didn't get actually. Is the 64 ASCII chart? I find it.
So you should probably look up a converter, not a chart, because doing it by hand would be pretty time consuming.
Waste more time than you want. The words kind of. What's the name of the Python function? Is it just decode and then you put in the basic? Is it like basic for decode?
Yeah, it's here. So there's a base64 module that has B64 encode and decode functions. And in Python 2, I think you can also just do like string dot decode base64 or dot encode base64, but they changed that in Python 3.
Make sure you separate by lines.
Yep.
Wait, so are those Python functions? Are they for like for objects? Like.
I mean, we'll get to it later on, but basically, like, these are just static functions. So you just like call them, you just do like base64 encode, and then in parentheses you put the string you want to
Yeah,
encode.
I'm just asking like, what do you call them all?
You don't call them on anything. You just import them from the module and call them directly.
Yeah, I'm just asking like, what do you like use the function?
Uh,
Sorry for not working out right.
yeah. Well, I can just like type up an example if you want to see. So, how do I do this?
I guess the input would be a letter.
Yeah. So basically, you do from base64 import these, and then
Oh, okay. Yeah.
oh my god, I'm sorry. Yeah. So basically, you use it like that.
That's one thing about like Python syntax I never understood. Like old, every time you use a byte, you always have to note it that way, right?
Yeah.
Is there a reason for that, or is it just for like readability?
Yeah. It's because it's actually a separate type for byte strings. This is something we're gonna have a workshop on later, so you can check that out. All right. So does anyone want more time for this? All right. So the solutions. The first one says hello in ASCII. It's encoded as a hex string. The second one says password in ASCII. It's encoded as base64. And the last one is beans in ASCII, also encoded in base64. So in this case, all of the data could be interpreted as ASCII. None of them were like images or sound files or anything, but this might not always be the case, but it's always something you should try to see if it's ASCII. So that's all. Uh, so this workshop is a little shorter because it's our first one, but that's all for today. If you're interested, join our Discord. I think everyone's on Discord, but you can join our Instagram, join our Get Involved. So thanks for coming, everyone. Also, just gonna double check Zoom chat quickly just to see if there's anything. Okay, there's nothing in Zoom chat. Yep. Yeah, we'll put up a topics list soon. We have it like roughly planned out, so we'll let you know. Uh, for now, no. We'll let you know in advance if there's anything you should download. Yep. So we will have a workshop later on about Python, but if you're interested, it's something you can look into yourself. Python is not a super hard language to learn, so. Yeah. Yeah.
So does having like a strong fundamental understanding like all the different, I guess, formats help like analyzing malware? Because I'm assuming that's how you compile it, right?
Yeah.
Like very little instruction.
So, um, what were you saying about decompiling? Sorry. What did you say about decompiling? Sorry.
Like, does knowing a lot of these like encoding formats not hard to help you like get through malware analysis? That's how you decompile, right?
Yeah.
Instructions.
So instructions usually like by the time you get to decompiling stuff, it's usually like outside of the realm of these kinds of encodings, but there's a lot of malware stuff that's going to be like hex strings or base64 because it's sort of a way to get around antiviruses. Because a lot of antiviruses will check for like obvious malware strings, but they won't check for the same thing in like base64 or something. Or, but I'm sure some antiviruses check, but then it's like a cat and mouse game where like, what? Maybe, yeah, but then there's like a cat and mouse game, which is like, what if I just base 64 this 100 times or something, right? What? Yeah, because you can just take the base 64 thing, and then that's just a string, right? So you can just treat that as a list of bytes and then base 64 it again. Yeah, so forensics ones are going to be towards the end of the year. So we're going by topics, basically. So, uh, Harris, I think. Yeah, so like all Yeah, so like all the tags we had are going to be things we go over in workshops pretty much. Yep, good night. Thanks. Okay, I'm going to stop recording.